A very good afternoon to everyone. All of you, welcome to the sixth day of ATAL sponsored online 6-day faculty development program on Outlook on best practices and strategies for chip design implementation from industry's perspective. I am very honored to introduce today's our speaker. Today's our speaker is Sri Raja Garu. He is working in Synopsys as principal engineer in Bay Area, USA. He is having 14 years of experience in semiconductor design industry. Now, I am handovering the session to Raja Garu.
Thank you very much, Krishnaveni Garu, for the quick introduction over me. Uh, Thank you everyone for a quick participation over this particular program. I'm very much keen interested to participate in this program. Well, first of all, I would like to know from Krishnaveni Garu whether you want me to present or you have slides to be presented. Andy.
You have to present, sir.
Okay, I'll do the projection. Okay, let me give me a second.
Welcome, sir. Welcome to the session.
Thank you very much, Andy. I'm just presenting my screen. Please let me know if you people are able to see that.
Yes, sir. It is visible.
Okay. So before going in, I would like to tell one thing. I don't know how the other presentation went forward, but in this particular 3 hours of session, I would also ask you to be interactive with me. You can stop wherever you want. You can ask me questions, and also please confirm me if you listen some echo from my side or it is clear.
You are clear, sir.
Okay, thank you very much, Andy. So going forward, you can stop me at any slide or any point or any topic we discuss. You can ask me the question and we can go forward. Even after the session also, we'll have few time. I don't know how much of time, but we can extend the things based on the things. Okay.
Okay,
And
sir.
thank you. So before going into all the semiconductor space or whatever you listen toward chip designing, I hope everyone is from electronics background. So I'll quickly start on the things saying that, see, today in the world, wherever you see, it's all about chips we have, right? Right from earlier days, if you see, there are very limited in the electronic devices and all. But nowadays, right from the smartphone or all the variables straight away from your specs to shoes, everything is smart. So once if they name it as smart, there is someone or something else is there in behind the particular device, right? So it's all about the chips. What it can perform is, I usually say the requirement or the problem solving skills comes from and brings this particular semiconductor chips. But in my way, if I want to say, the basic thing is, if there is some problem, people go there, approach it, make a solution for that. In most of the electronic spaces, there are two-way rounds. One is problem solving, and other one is, you can say it as, you know uh, the laziness of the human being. See, because in the at least couple of years back, people used to go to switchboard to tune the fan regulator. But nowadays everything is smart. You can control your fan with the your mobile or external remote. So there are two sides of the coin. So in the same way, people utilize this, and the same technology has been making humankind lazy. But anyways, round to coming to the electronics, we build many and many chips making this problem solving things. People call this even solving the laziness kind of thing to be a problem solver, and people make designs and chips. So to confess the things, it's all about, you know, problem solving and making somebody else do our work. And in the most of the devices, whatever it solves the problem, it's all about, you know, computing. So when we see these particular global computing systems earlier, when we were like at least 5 to 10 years back, we used to see these computer resources, right? In the nowadays the IoT devices, mobile phone, tablets, PCs, laptops, printers, washing machines, whatever you call it. Earlier days, we used to see only these kind of things. But nowadays, right from your specs to your blast light, the ring, even the wearables, the clothings, and even the shoes has become smart. So shoes itself can count how many steps you are taking and all. And even the variables, the ring also counts your blood pressure, your heart rate, and it sends to the mobile and it updates it. So if you see, there are a lot of things, a lot of luxury items keep on being added to the humankind. So this all comes from the requirement built by the human being itself. So whatever the system you take, the basic funda is just, offloading your job. So in the same fan regulator case, rather than you going from point A to the switchboard, rather you go there. The only thing is you sit at the same point A and use your mobile or use the remote and control the fan, right? So in the same way, somewhere or other, all the devices, all the electronic devices, in the most of the case, it reduces your job. That means the workload of you or the human beings has been shared by all the systems or all the devices, I can say. Right? So whatever the system or whatever the device it may be, it offloads for you. So it does some job for you. So every device or every electronic gadget has a small or minimal brain based on the workload it bears. See, for example, you have a washing machine. Washing machine has a smaller brain when you compare it with the laptop, because washing machine, whatever it has to be performed, it is like it need to spin the drum, make some drying process, make them, spinning, drying, and washing process, then water inlet, water outlet. This is what it need to offload you. Coming to the phone or the PC, it does multiple tasks for you. Like you can watch movies or play games parallelly. You can work. You can demonstrate something. You can talk over things. It does multiple tasks. As most of you are aware of what is difference between controller and process, those all things we are not going to talk. But we are only talking about the offloading of the structure. See, whatever the structure it may be, the same thing. Something or other ways it offloads you. See, what I always say is you need to say something as an input to these particular devices, and it offloads the task for you, and it gives the output based on the individual device. So for this example, we will talk at least two or three different kind of things. Okay, we'll talk the very simplest, we'll talk little bit higher one, and we will talk very higher one. Okay, so now let us take the example of your computer or the laptop. So whatever the inputs or whatever the offloading you want to do with the help of the PC or the laptop, you generally pass some inputs using keyboard, mouse, etc. And then it does or performs some task for you, and it displays the output whatever you want onto the desktop or onto the monitor, right? In the same way, if I take the same example of uh, washing machine, whatever talked earlier, we give some inputs using the keypad, whatever is present on the washing machine. When you press some button on the washing machine, it understands it, it takes the input, and based on your inputs, it performs this task like rotating the drum, water intake, sorry, water outlet, and do some spin and dry kind of thing. If you take the same simpler thing for the calculator, it is also same, right? You have some keyboard, you have some display, you enter some numbers, you give some addition, subtraction, multiplication, performance, whatever you want to do, right? Then after it will display whatever it want to display onto the screen or the display it has. So whatever the device you take, you give the input whichever the way it can understand, Okay. So based on the input, it does something and it reports it back. So that's all the system is. The only thing is how much workload it bears. See, every processing system or every device has a minimal brain. Whether you have controller or processor, even controller have processor. You all know that. So if you talk all about in the wording of processor, it's all about the workloading of the thing. See, the washing machine or the calculator or the projector also have the uh, processing capacity, but the thing is workloading is bit different when you compare it to the laptop. But why we generally you do not use the same processor of the laptop is, of course, the costing of the things, right? The processor which we use in the PC is much more costlier than the washing machine processing system, and we don't require that much amount of processing happen at the washing machine side. So we want a lesser area, less power consumption, high performance with lower cost. That is all about electronics. So now if you see whether the work bearing of the thing, whether it is very less or very high or very medium, the thing is the processing or workload sharing is common. So if you see the below diagram here, we have a minimal processor. So now we will discuss. So now we will discuss only about, not about the how much workload it can bear, but we will discuss about how the processing of this workloading happens. Okay. So in every global system architecture or whatever the edge device or the product you take, the basic minimal thing is we hand over some data to the particular offloading person, right? Whatever the things you want to tell him, you always tell him with the use of data, right? And then it's all about digital system processings and all. So I'm not going to that side, but as you people know, it's all about processing the data. So we need to pass some inputs to this and understand things, and that's how you come outside, right? So whatever you see here, there's a programmable interfaces right here is a input output. You can just think as a input output ports where you pass on the data to the system and you get the data as output from the system. If you think simple calculator kind of thing, you have some keyboard to input the data, sorry, keyboard to input the data, and output will be the display. So if you see whatever the data you are passing from the input system, it will come on the data bus. So in any processing system, this data bus is very common where we need to handle things about the data. Then coming to the address bus, to address the existing devices on the system, we need to choose. It's similarly kind of a rule number which you use in the class with the students, right? So whenever you want to call some student and offload some work, you call with their rule numbers. Similarly, the address bus does the same. And apart from this address bus and data bus, we have one more thing called as control bus. It has many other control information. For example, one of the things we can talk is like, see, for example, you want to read or write inside this particular memory. Then you need to say whether you are doing a read or write to the memory. So these kind of things, apart from the addressing and all, we need to form these kind of things onto the control bus. So I know this is very, very basic things, whichever we are talking, but I wanted to start from the basics and then go through the topics. Okay. So then earlier days, if you are aware of, then we used to have a motherboards where it used to have many of the chips like this on this particular board. But ongoing onto the things, people came up with a new concept called system on chip, which is nothing but whenever an product company. So before giving that, I know you are aware of embedded things, what is going on, and VLSI side, what is going on. If you're not aware of, anyways, I'll just give a glance and come back. Okay, here. So whenever there is a product building company want to build something, they always give some choose some IPs or choose some ICs or VLSI ICs from different companies. So for example, if you take Dell want to make some laptop for students. Okay, their budget is this much. They want this much processing speeds processor, and they want this much specifications of RAM, SSD, and all. Then they give this spec to the architect. So architect defines what kind of processor you want and what kind of you know the GPUs, the DSPs, whatever the different blocks it want. Then it comes to the VLSI companies. Let us check here. They'll give an opportunity to Intel make a processor for them, which should be of this much speed, this much cost, this much area, and all. Then they start building a chips, or if already the chip exists, they give that chip to the Dell people. So other way around, once they make the chips, the Dell people again collect back the chips and make on the motherboard. They integrate together, the PCB engineers and the embedded engineers make this kind of structures and make a product and sell it, right? So earlier days people used to do in this kind of format only. So once we also discussed that for us in the electronics, it's all about speed, area, timing, I mean, the power, and also the cost. So people came up with this concept called system on chip, where whatever the different ICs you are seeing here, this form a system. So they bought all the systems of IPs onto a single chip called system on chip. So the main difference is once you have these two IPs, let us take IC1 and IC2. Okay, if you want to communicate from this IC to this IC, first of all, this is all processes in the digital format, and this IC also formats. This IC also operates in digital format. So you need to convert this digital to analog, then onto the analog pins, whatever you are seeing here. Then from the PCP routing to the background, again it goes to this analog pins. Then again it converts into digital. So basically, digital block to digital block. If you want to communicate, there are digital to analog conversion, then onto the wires, then onto the analog to digital conversions, which not only bring the you know the noise things or power issues or capacitance kind of issues into the picture, but also the speed differs, because when you're converting from analog to digital and when you're going to the real world onto the pins, there are these kind of capacitance, noise effects, and all. You can't operate on higher frequencies. So to speed up the frequencies and all, they brought out the new things called the system on chip, where they eliminated this process of analog to digital to analog conversion, back to analog to digital conversion, and these pins. So whatever the digital block you see here and whatever you see the digital block here, they have integrated onto the single chip, and they named it as system on chip, and where you can directly communicate between the block to block from digital to digital itself. Because of this, the speed has been increased, as you don't have analog to digital conversions, digital to analog conversions, and pin things. And next, for the same reason, the cost is reduced, the power is not there, power is reduced because of the same conversions and pin level things are not there. So the speed is increased, and cost came down, because you don't have many blocks and you integrate it into single chip. So the fabrication things also matters. So whatever the device you are seeing today, everything, most of the things has came up with this kind of system on chip. That's why whenever you go to the service centers, earlier people used to replace this kind of smaller chips if they have some issues. But nowadays when you go and talk to any of the service guy, he just say that this has some motherboard issue, so you need to throw this out and put a new motherboard, because on the motherboard you see only this one SoC, the application specific, the complete system on a single chip. And if you open the board, you don't find anything else. So rather than knowing what happens in the chip, just throw out the chip. Just rather than pulling out the chip and putting it again, soldering and all, rather than you can throw out the board and put the new one. That the main way, that is the main reason why, people are saying, complaining about they have some motherboard issues. And because of this, you can see many of the embedded roles have came down, because even VLSI guys has pulled this role in. See, earlier people used to collect the ICs, put it together, and do all kind of testing whether it is working or not. This all comes under the embedded engineer role. But as on today, people has pulled it down, kept everything in VLSI. So, so the roles also came down. So this is about SOC. If you see here, we have an example SOC from NVIDIA. So this, as you know, NVIDIA is mainly majorly deals about, it's all about graphical units, processing of video, audio, and all. So, sorry. So every system will have some processing units. So earlier, whatever the systems you are seeing here, the CPUs, video processing, signal image processing, audio processing, HDMI, and graphic processors, everything used to be a individual chips, like whatever we saw here, right? So people brought all the core, all the things onto single chip, and they named it as system on chip. So whenever you are communicating between these two blocks, everything is digital to digital, and people called it a system on chip, right? So whenever they bought all the ICs into the system on chip, they named these all individual blocks as subsystems. So as this is a complete system, they named this as subsystem. So subsystem forms SOCs or systems, and inside the subsystem again they have something called as IPs. So so for example, we will take the processor itself. So processor itself, or CPU itself, will have multiple smaller blocks which has its own functionality. Let us take ALU. ALU has its arithmetical logical unit, you people all know. So it has a specific task to do. It has a specific function to do. So people form this kind of IPs to make a subsystem. Earlier, the same thing used to form as ICs. Now they form it as subsystem, and these subsystems form SOC. Okay, so when you see these particular things, we'll go into next slide. We have shifted to next slide. If people are not able to see the next slide, please let me know.
Yes,
Okay,
sir, it
as you
is
are.
showing.
Okay, thank you. So if you see here, there are many of the different kind of systems you can see. So it's subsystems you can see, sorry. So whatever you see it as DMA, camera interface, EMAC, USB, graphical acceleration card, LCD controllers. These are all the common terms which you generally see, and we have many things like CAN, USB, SPI. So we see many of the blocks with different interfaces. See, for example, you take a projector or you take a display, you have a HDMI cable, you have a UART. So there are multiple ports you see as outside. Similarly, in the inside, for processing of the things or to make something to work on the block side, you have many other subsystems also. Okay. Okay. So when we talked about IPs form SOCs. So IPs form subsystem first, subsystem form SOCs. So when IPs to IPs we want to communicate. See, whatever we talked earlier, the processing is all about data. So when you want to interact the data between different IPs or different blocks or different subsystems or different SOCs, or even after SOCs to SOCs, the main thing is protocols. See, protocol is nothing but, I hope the people know, but we are recalling things. So protocol is nothing but you form a set of rules to send this data, or to hand over this data between the two entities. Okay, we can call, rather than calling the data, we can call it as information. Okay, so two entities, in between two entities, if you want to send or transfer or receive this input information, you need to form some set of rules, because the other IP do not know when you give the things or when you take the things. That's about the information. So people make this protocol as a standard. So we have many of the protocols which you see here. Even this block, if you see, we have camera interface, we have DMA interface, we have EMAC, we have lot of interfaces. So if, for example, even if you take a computer, you have Ethernet, you have HDMI, you have USB, you have many other things. So when I ask why we need this many protocols, see, it's all about sending or receiving of the data. So if it is all about sending or receiving of the data, you can use the same protocol. So for this, I always give an example called a road kind of thing. See, in the college, we use 30 feet road. In the parking of the college, we generally have 60 feet road. And on the highways, we have 100 feet road, right? So everything is road. But the thing is where the it utilizes. See, in the college, only students will be using the road. In the parking, you have cars and bikes of students and faculty. Then onto the road, you have lorries, buses, cars, and much more things which you utilize. So even everything is a road based on the requirement and based on how is the traffic over there and how many people are using it, what type of people are using it. We different the road, right? The size of the road. In a similar way, protocol is also differentiated in their how much amount of data you can transmit in this particular time is the main thing. And second thing is on how much speed and the same thing cost you the same thing also make on the cost front. See, if you have a USB is very small protocol compared to Ethernet or PCIe and all. So the costing of the USB, that means the handling the data from the left to right or one entity to the other entity, it need a minimal logic when you compare to the Ethernet or HDMI or PCIe. So the costing is less. So in the same way, wherever you want 30 feet road, if you use 100 feet road, it wastes your space and cost and area. In the same way, the protocol also, if you use the bigger one, it's all about the cost front, right? So as I already told you, we always need to make it everything in the lesser cost with higher speed, low power and all. So based on the requirement, how much amount of data you need to transfer from point A to point B or between the entities or between the subsystem or between the socks, architects decide that and use the particular protocol. Okay, so this is about why we use this many number of protocols into the picture. So similarly, as a kind of road winding concept, so whenever the size of the road is not feasible, or if the traffic is very high on there, we go over and increase the road size, right? In the same way, we also have different levels of protocol versions, or people do this road winding in the protocols also. For example, earlier we used to have share it. Share it application used to be one of the application to transfer the data from one mobile to another mobile using Bluetooth. So earlier, if you want to share something over share it used to take some file is around 1 hour of time. Then share it came up with a new concept called Wi-Fi. So whenever they shifted to Wi-Fi, rather than sending from the Bluetooth, they have tuned to send the same data from the Wi-Fi. Then the speed has been increased, and most the same amount of file is taking very less amount of time when you comes from the Wi-Fi, right? In the same way, people also based on the it's like same like a road winding concept. Whenever whenever their things are not sufficient onto the bus or onto the sending or receiving of the data, then they go up with the higher versions of protocol or modify the protocol and all. So that is the reason why even on the latest hard disk, right? Earlier, if you want to use hard disk, people used to have SATA cables where you need to connect the SATA onto the motherboard and you used to transfer the data. Then people came up with a new concept called SSDs, not only onto the solid state drive side, but also onto the protocol front. They have removed SATA and they have introduced PCIe. Like PCIe is the older one, which is already using in some other applications, but they brought that protocol, they attached it in place of SATA. So that is one more reason why you have very high speed over the SSDs. So here take to I would ask if someone has some questions onto the protocols.
Why SSD is having a more faster than hard disk, sir. Hard disk.
Okay, there are two things. So one thing is earlier when hard disk used to be the state. So when you have a hard disk, right? Internally, if you open the hard disk and see, there is one disk similarly as CD inside the things, and mechanically used to mechanically and electrically they used to store the data into the hard disk, and then they used to send the information from this hard disk to the memory, and then they used to send the information from this hard disk through a protocol called SATA to the mother to the whatever the processor and all, to the motherboard, then from the motherboard to the processor and all. So there would be a much more longer process, and it used to take some time. See, earlier the speed was okay. When people want much more speed, they find that there is a bottleneck going through SATA and communicating over hard disk. Then they brought out a new thing called you can communicate over PCIe protocol, which is a very faster protocol compared to SATA. Not only that, onto the storing part, rather than storing in the hard disk, they have brought out a new concept called storage devices, and that's how they have used. And when you compare, that's why the speed has been increased. So everyone want a higher speed things. So today processings, whatever you do, first of all, you storage in the primary area, then you go to the secondary area. So secondary drives, the hard drives or SSDs, if they are taking time to read back and all, then that's a bottleneck. So that's why people came up with a new concept called SSDs.
Okay, sir. Thank you.
Any other questions? Okay.
You can proceed, sir.
Okay, thank you. So as we see from the earlier point of view, so all it comes from the requirement. So requirement forms individual ICs earlier, but today they made it as SOC, and based on the requirements and based on the speeds and all, to communicate in between these blocks, we generally use protocols. So once you have some requirement from the architects saying that this is the VLSI IC which we are going to develop, and these are all the blocks which we have, and in between the blocks, these are all the things. So architects and sub-architects, they begin, they divide the things like block level, subsystem level, and SOC level. What are all the things need to be done, and they form uh, all the documentations for that, and what functionally how it performs. See, for example, you simple take it as a adder. Okay, you need to have this many inputs, this many outputs. Okay, this should be this is kind of the adder, and what kind of adder it should be and all. They write in that level onto the very smaller blocks, then to the subsystem things, then to the SOC level. They make it as the documented, and we generally call it as design specification or design document. Then after getting the document, they give it to the RTL design engineers, where the picture comes, where the RTL design engineer picture comes there. Okay. uh, so earlier, I am not sure if you are aware of mm, how the VLSI flow happens, at least on the front end side. Back end side, I guess Dilip already gave the things, but front end, I would like to give much more in detail. Okay, I would like to use some uh, paint, or I'll use the same thing. I'll create one of the empty slide. So once, so we have different kind of structure, especially in front end. So once you have architects and sub-architects, architects architects always take care about how this chip should be, the size, the power, the speeds, and what are all the subsystem it need to have, what are all the ip level, soc level, subsystem level specifications. All these kind of specifications will be given by these architects only. Okay, so once the architects make the specifications, it comes to the low level people called sub architects, who is under this architects, where they take care about uh, all the IP level or subsystem level or very basic things, what type of IPs you need to use, what are the different protocols you need to have communication between the two IPs and all will be taken care by these sub architects. So once they make the documentation and all, next the role comes with the RTL engineer. So RTL engineer will take care of executing the design kind of things, like, so based on the whatever architects tell, right, how the IP should be, what is its exact functionality, they will mimic them in the code. Earlier, when our design engineers, or we generally call it as design or RTL engineers, earlier they used to make the things with the fets and all, to fets to the IFCs level, then onto the uh, board level, and then onto the PCB level and all. That's how they used to do. But when once the Verilog came into the picture, it has been became very easy, because rather than you are understanding the logic and making that logic realize on the uh, real fits or gates or whatever you use, rather than doing that, this particular new language has been there as a mediator between you and tool, to understand the tool, so that you just tell me the logic, I'll make the implementation or the gate level or uh, fet level things for you, right, rather than putting one gate after one gate and checking if the functionality is correct or not. You can just uh, give me the behavioral things into coding, where the tool can understand the code, and based on the code, it gives the synthesized output, like what are the gates you need to be connected, type of the gates, and how the connections between the each gates happen, everything comes from there. So once this is done by the RTL engineer, uh, I guess some disturbances. Fine. So once this thing has been preached, we have design verification engineers who are in parallel with RTL design engineers. Okay, who generally takes the same spec from the architects, understand it, and verify if it is functionally correct. See, for example, you have simple adder, and architect want to make a simple ALU, for example. Okay, this is this much bit in ALU, and this have this many inputs, this many outputs. Functionally, if you send something as 0x00, it will do like this, and if you send something, it need to do like this. That design will be made by the RTL design engineer. But at the same time, verification engineer also understand it, so he make the other side test bench ready, saying that really if you pass this kind of inputs, are you getting these outputs or not? That is what he generally tests. So for that he don't see the RTL code. Sorry, give me a second. For that he don't see the RTL code. Rather than that, he understand the specs, and parallelly he make a design. Okay. Uh, for his reference, then he see passing on the things if he's exactly getting the output whatever he has expected. So whatever the design verification engineer is doing, he's using the same simulation tool. Wherever you write the Verilog, you pass the different kinds of inputs and checks the outputs. That's what he do. So in the easy checking in the realistic scenario is no, because whatever he is checking is functionally the written code by the RTL engineer is correct or not. That's what he do. But to mm, uh, but sorry, your voice is breaking. Is someone speaking on the call?
No, sir, it is by mistake.
Okay, thank you. So, so this design verification engineer uh, is always verifying functionally, like the written code, whatever he has written, uh, is it correct or not? I mean, functionally, it is giving the expected result or not. So, what people do is, in parallel or after this, people bring the same thing onto the FPGA engineer role, where you have a FPGA engineer. Okay, so what he does is, I hope everyone knows FPGA. So whenever you put the same design onto the FPGA, as it's a field programmable gate array, it has many basic components, basic building blocks of all the gate level, flip-flop level, and muxes or whatever it is. It's all have all the basic building blocks. Once you put the design or whatever the RTL code you write there, it makes synthesis implement the same thing onto the FPGA. So it will mimic your hardware, and exactly whatever you written functionally, the FPGA behaves as it once you load the bit file on top of it, right? So once you have bit file on top of it, it is like your logic has been on the real world, which means it has all, at least not the 100%, but onto the most of the percentage of the all the uh, electrical impacts or the error scenarios or the real um, you know real world, talking to the real world and all these all things you can put it on the FPGA and check. So once people has the RTL design, or in parallel people generally do this FPGA verification also. This is generally done by the FPGA engineers, and in some cases the same RTL engineers will be doing this work. So so in the realistic scenario, we're checking. So design verification engineers will check on the simulation in the only the simulations. Sorry. So design verification engineers will only check on the simulations, and mm, so FPGA engineers will do the same kind of verification on the FPGA. The only thing is, at least design verification engineers can see what is happening in their code, because they can always pull all the signals and all. But FPGA engineers has a very limited addition, because you don't know what is happening inside the chip. But there are some other debug options which we can use when you want to do it from the FPGA. So once this ongoing thing happens in parallel, we have one more kind of engineer role. Okay, onto the front end especially, we call this engineer as GLS verification engineer. Okay, so in some cases, this GLS engineer also will be one of the design verification engineer only. That's because, see, once you that we always nowadays using the tools uh, to whatever the code you write into the Verilog, at the end of the day it should form into gate level. Okay, so once you make the synthesis, it goes to the gate level, and then we also not sure if the tool itself has some issues. So based on the whatever the code you write, it can mimic in different ways. Sometimes tool also will not be much more matured, and it also can make some mistakes. So rather than figuring out this, people what they do, post synthesis. That means once you get the netlist, have all the gates, all the wires connected onto the gates, people pass some inputs, whatever you did on the verification front in the design verification. Similarly, they pass some inputs, check the outputs. In a similar way, you do these design also. But the difference is, here you make your check it functionally. Here the difference is, you verify it on the gate level things. So once the gate level thing is available in as a netlist, then you pass the inputs, all the scenarios, different kind of things, and you check the things. So earlier we told that the IPs uh, form subsystem and subsystem from SOCs. As once the SOC is ready, that is the whole and chip which we give to the product based companies who are make product, okay, or the end devices who are want to make end devices. So on the every stage we need to verify thoroughly that is everything is good or not. So that is the reason why you generally do verifications on the three levels. One is the IP level, subsystem level, and the SOC level. As we earlier see, IP, subsystem, and SOC. Each and every level we have the specification of the functionality, how it works. So people pass some inputs, checks the outputs and all. The same thing will be repeated on the IP level, subsystem level, or SOC level. But the difference is, as we discussed, everything has some inputs and outputs. But functionally, how you pass the inputs and what you expect as outputs generally differentiate based on the functionality the block has. So in the same way, they understand the things by the spec which is given by the architects. Then they perform all this kind of things. So design and verification engineer do that, and FPGA engineer do that, and GLS engineer also do that. So once you happen this, then from here you have the different role like DFT engineer. Okay, so where people will have debug related IPs as cancer related IPs in this. So DFT engineers also have uh, the, the main thing is to implement the it's all about design for testable C. See, for example, once the chip is ready and you tape out. Okay, so once it is ready, people don't know what exactly happens inside, and once your product is ready, if you find something issue, you go to the service center, right? So there, people generally, plug in the USB, understand the debug things, what is happening inside the chip and all. That's because of people like DFT engineers involving few of the um, methodologies or technologies or IPs inside the chip to know the health of the chip. So this the engineers have different role. Like this, you have many other engineers coming into the front end and back end. So here I discussed about very few engineers. So why, if you see, for example, you have whenever you get some issues in the design verification, you come back to RTL engineer for the fixing. FPGA engineer fights something, then if it's an issue, it comes to RTL engineer, you fix it. GLS engineer, same again, RTL engineer fix it. DFT engineer, something's they need to talk with the RTL engineer and fix it. Then it goes to the PD. I hope those engineers are covered there. The physical design engineers or layout engineers or the implementation PNR engineers, static time analysis engineers. So whatever they do, if they want to fix something, again they come to the RTL engineer. Then RTL engineer will fix it. From there, the cycle again rotates. So you do a lot of things with the RTL. So if you just see, if one RTL engineer is implementing something, there are many and many verification engineers or other engineers check whether he is really doing his job correctly. So that is the impact of RTL design engineer there. See, because if something this RTL design engineer makes a mistake and design verification engineer could not figure it out and he just left the things, it got in FPGA, for example, then again the cycle repeats. If it happens in the uh, timing or at the place of timing or the place of PNR, then again it comes onto the RTL design. We will talk why it comes on the timing front and on the implementation front, why again it comes to the RTL engineer. Okay, on the next things we will talk. But once it come to the RTL engineer, it his responsibility to fix it and give it. Then again, these all people, whoever is there in the chain, need to do their job, because if something fixing in the RTL may mislead and something else also may go wrong. So there is a chance. So people in the VLSI generally do not take any chance, because the life cycle of the chip is very precious. See, for example, I'll tell you one of the incident happened at one of the top companies. So for example, if you have some issue in the software, right? People generally give a patch or generally give some release saying that, hey, you have a new update, just update it so that um, mm, this will be working. That's what software people do. But if there is any issue in the hardware, okay, there is nothing you can do. You need to replace the chip. That's what if somebody tells. So no, that's very burden to the companies, because see, there is some issue happened at Apple some long back, okay, saying that hey, this is the issue which we can't fix in the software. Only thing is you need to go back, to figure it out where the issue is inside the chip, fix that bug, and tape out the chip again, put that in the device wherever you have, and give it back. This is the issue which has happened to the Apple company some long back. uh, and to fix or find the issue and make the fix it, and go through all the steps, verify everything, and make sure everything is good, and make the chip to tape out level. It almost took 3 years. It's almost like 36 months, 3 years for a Apple company to do that. See, if Apple, a giant, very big giant in the VLSI, if the Apple itself took 3 years of time, just talk about all the small or medium range companies, how much impact it may cause. Because not only onto the fabrication cost or testing cost, you have this many number of engineers working on that particular projects, and each different kind of engineers will have the manager level, team lead level, junior engineer level, senior engineer level engineers. They need to pay the cost or pay the salaries to them. Okay, then it's all about number of working hours. So it took almost 3 years to fix the chip and respin it and tape out. In the similar way, for the R&D of the same chip, it almost can took 3 more years. It's nothing. Nevertheless, like almost 6 years, this many people working on the chip, this much investment going in, and at the end of the day, if it's simple a failure of the chip in the market, there will be more talking saying that hey, this product has some issues, so we should not buy it. Then there's this small kind of more talk will make the company into losses, right? So that's why nowadays the respinning of the chip uh, time came to down. But earlier days, even from last 2 years also, before last 2 years also, it's almost it would take 3 years minimal to minimal to make some chip out or the tape out. So that's why if you see junior level of engineers whoever joined the company, even in the product or in the service or wherever it is, people say like until and unless you get 3 years of experience, you will be considered as junior only, especially into the VLSI. The reason because is if the new joinee want to see some the complete cycle of the chip tape out, then it may take 3 years. Because see, for example, there is some issue caught on the STA, then STA guy comes, talk to the RTL guy, make it fix. Then again, design verification engineer understand it, then cross verify it, and he need to know how we missed it. Then it goes to the FPGA engineer, then on to the GLS. Then this process will be repeatedly happening, right? So that's the reason why people in general, take time, and even as this costing is high, so that's the main reason entering into the VLSA is bit tougher. And even if you enter, you still considered as a junior engineer, even you are 3 or 4 years of experience. By the time if you go to software, it is like a you'll go to the at least onto the second level after you're joining under software level. You call it as level 2 engineer or senior engineer or whatever onto the software front. And people are investing this much amount of money, and they don't want to take risk of chip failure, because once something has went into failure into the VLSA, it's a boom, it's a gone. See, once upon a time, if you remember, there we used to have uh, every house used to have a Nokia phone, some long 10 years or 15 years back. But today, uh, you don't have Nokia phone brand itself. It's very, very minimal when you compare. So in the VLSA, it's all about you are into the market, you keep on updating, and you make your products updated. And also, you should not have any failures in the market. If once it make a failure into the market, it can collapse the company. So that is the reason why people in the VLSA on the top management, they don't take risk, and they always want the senior guys to handle the things. And also they put many of the verification guys, many of the GLS. And one more thing is, if one design engineer you have, you will be having four verification engineers to cross check if everything is correct or not. So in the complete thing, so design engineer or the RTL engineer has much more impactful play into the complete chip designing, because if he makes something wrong, everything will be collapsed. And if somebody else also did not caught his mistake, that is also a big issue. So these are the reasons why, into the VLSI is very tough to enter. Even you, if you enter people like juniors, why you take much more time to become established in the VLSI, and why you have many verification engineers compared to design engineers, right? So these are all the reasons, and why generally why VLSI companies don't take a risk of getting juniors on boarded is, this is of the main thing, right? So any doubts so far onto the uh, RTL introduction? I mean, the different roles in the, especially on the front end side, and why you getting into the industry is much more tougher, and what are the opportunities you have today and all.
Which tool is used for GLS verifications?
Okay, so in the Synopsys only, you have tools like, even in the Wordy, people use the GLS verification. So Synopsys Cadence also has their own tools.
Okay.
And if it's a functional, if it you have something onto the automobile side, like if this chip is going into some car design, then people used to, there will be one more engineer who takes care of functional safety verification. We generally call it as FUSA. Uh, there is one more tool to do that. It checks whether functionally everything is correct or not, because for not only on the functional side, on the safety side also it takes care. So we have something called on Jasper, also a tool name there, which we generally use for fees and all. So we have many engineer roles into this particularly. Any doubts on this front?
Nowadays, for verification, uh,
Hmm.
is you are using system Verilog only?
Okay. It's a good question actually. So yes, we are using system Verilog only. But in most of the cases, it's a system Verilog. But parallelly, industry is going towards to the very much more higher level languages also. We have something called as HLS. It is onto the RTL side, but people, if you ask, really people are using it today? No, but people want to migrate on much more higher level side. Even people want to use C++, Python kind of things additionally onto the verification side, but still they are in training, trial and error methods only. Yes, today still we are using system verilog, but the thing is, on top of system verilog, we have something called as UVM and OVM. It's just a verification methodology saying that, see, if you want to drive, if you want to do something, then you need to follow this kind of structure only. So if we have some time, we will see that some structure, I did not put that in the slides, but we'll definitely see how the structure is, like why the structure is confined to this methodology and all.
Okay, sir. Thank you.
Thank you. Any other doubts? See, I like to have this section more interactive. So once you get some doubts clear, that would be very helpful for the students also to understand real things onto the VLSI. So feel free to ask me any doubts, whether it's small or big or whatever it is. I hope no doubt so far. We will get into the RTL design. Okay. So now I know. I think you have the understanding of the why RTL engineer role is a bit complex, and he has much more responsibility on his shoulder when you compare to all other engineers. Is like whatever he made the code ready, that is what is mm, go into the chip, and functionally that is the selling product of the or selling USB of the USB of the company, right? So for the RTL engineer, the main thing uh, is before going in, the logical thinking or logically the capability of thinking things should be very very high when you compare to all other engineers, because when he write the code he need to understand all the possibilities, like how the things will happen and all. Okay, so we generally call it as register transfer level, the RTL design. But earlier, if you see, people used to connect the fits all together to form a design. Then it is becoming very burden, because it's a keep on forming the fits and all. It's very bigger design. Then people came up with the gates where you have fewer fits form a gate, and people came up with the gate ICs, like you have a IC of four gates, then you put all the gates together, all the ICs together, then connect in between these ICs, sorry, and form the circuits that they would do earlier. Then by which the size of the design or the size became very very high, where you need to sit and integrate together, put the design together and verify it and all. So once it became the hurdle, then or it became the bottleneck, then people came up with this new concept called, hey, you just let me know the logic, then I'll make the synthesize things for you. So even in the even in the Verilog coding, people started with the gate level things, then onto the data flow model where so in the gate level model you just write gate, and you have FET level also, and you have gate level also. Then you in the gate you just say this is the input, this is the output, and you connect between the gates and all. Then it came on to the data flow level, where rather than putting gates, you have for each and every AND gate or gate and all, you have a variable. You just say A and B. So if C is equal to A and B, it will put a AND gate between. It will put a AND gate as A and B as inputs and C as output. And then people came up with much more top level perspective, saying that, hey, no need to tell me the thing also, logic also. You just tell me the functionality. Okay, if this is the functionality, what do you need to do? If this is the functionality, what you need to do? Then people came up with the behavior rules synthesis thing, where you just write with the using the simple if, else, and for loops and all, with the loops based on things which it will understand, and it gives in the realization in the form of gates, and that we call it as synthesis. Right. So identically, when you see about synthesizable code and the software code, see software code or software guys, can write the code in different ways. See, if you take the same if loop, people can put multiple ifs, multiple things, and if they don't care of else also, it's not an issue, right? See, for example, we will see the same example for the if code. Okay, see, for example, if you write like this, uh, in the software, if you write if case, say for example, if a is equal to 1, then do this, and you don't care of else case, right? You always don't care of else case. But in the real RTL thing, if you don't care of else case, this can lead to some other hardware things. Okay, I can show you this, so the Google itself, so some of the example we can Google also. See, we will take the same example of mux. Okay, I guess they will explain this, but if not, okay. They explained about if and else skip. That's okay. Never mind. Okay, let us take uh, the same example. Take it some other thing. Hmm. I'm sorry, I didn't get much time to pick up examples and put in the PPT, so I thought of directly showing whenever I want to talk with you. Okay, okay. That's okay. I'll draw myself. Okay, let us take. Let's take if I written a code like this. Okay, don't care of capital and small because I didn't modify it. Okay, if okay, so if you just put if A is equal to 1, B is equal to 1, that's all we put, which means whenever we feel like, okay, if you have some if you realize some hardware for this, so you have a mux, okay, and B will be the output to the mux, okay, so you will have some input, so mux has some inputs, okay, I'll make everything is white. Okay, so you have some selection line. Okay, so the same thing if you have uh, let us check, this is the so this is A, and if this is B, okay, so if you think this is as mux, okay, so whatever the code you write, if you just say if A is equal to 1, so if the A is equal to 1, you just think that you will have um, you'll directly tie this to 1, okay, you generally tie this to 1, so whenever the A is equal to 1, as if the B you will get it as 1. That's what in general implementation, if a software engineer write, it will be like this only. But ideally, if you do the same thing as synthesis without the else thing, and if you just write, what really it happens is you'll have a latch here, okay, and this latch always take the input from this, okay, and then again the same thing. with whatever the secondary input of mux you have. Okay, so from the latch, so you'll form something like this. So if you don't write a else case, it is like the hardware will realize in this way, like whatever the output you get, it will latch, and they again it will come as a input or the secondary input to the mux. So the if you take the first case, you don't see this latch, and you just think whenever you pass some input as one, whatever the one is there will drive to the output to the B. But that's not the case. If you directly write as a real hardware kind of thing, the hardware will realize in this way if you don't write a else case. The same thing will be a replica for the case statement also. If you don't raise a case statement, the same thing, defaulting in the case statement, whatever the inputs has been missing, those will form a latch thing to the uh, mux. Similarly, when hardware engineer write some piece of code, he need to have a realization in the mind, like whatever you write, what hardware it forms after synthesis. So because the same thing will be happening onto the area front, onto the uh, timing front also. See, because for example, onto the timing front, we will talk about one more thing. Okay. uh, See, for example, you take the same thing. Okay, you don't have all this. Let us think you have the AND gate. Okay, some code you have written, and let us think this is the AND gate. Okay, you have two inputs and one output. I'm not bothering about what is the input and what is the output. Okay, so for example, you have two inputs and two outputs, and if you came up with a logic like this, where you have one gate in this way, where you have A, B, C, D. That means A and B and C. Okay. If you write a code like this, okay, let us take D is the output. D is equal to A and B and C, and if you put four things for an example. Okay, that means you have one more thing in this way, right? So like this, it used to form a thing. So for example, each AND gate have a delay of 2 nanoseconds. Okay, so 2 plus 2 plus 2 plus 2, it's all about 4 AND gates multiplied with each 2 nanoseconds, which means to pass a value from here to here whenever you apply some input, the worst case it takes is 8 nanoseconds, right? So rather than putting like this, okay, based on the code you write, okay, if something happens like this, so a b c d you can pass here itself. Okay, so you can pass here itself a b c d, and the same inputs will be driven to all these two AND gates. So the same three AND gates, the circuit has been realized where the you know number of gates has been reduced to 3 rather than 4, and also the delay has been reduced because if it has same 2 nanoseconds delay, to these 2 nanoseconds and this 2 nanosecond will be in parallel. So which means when you have some change in here, in the worst case, to pass till this inputs, it's only 2 nanoseconds, and from here to here it will take 2 more nanoseconds. So overall it's only 4 nanoseconds. In the earlier case, if you remember, it's all about 2 plus 2 plus 2 plus 2, that means 8 nanoseconds with the 4 gate. The same logic here you have is 3 AND gates, I mean 3 gates with the delay of only 4 nanoseconds, so it is reduced. So if you want to get the similar kind of thing, then you need to code in this way. Sorry. So based on the logic, So based on the logic you write, the implementation changes in the synthesis, right? So so how you write, the tool understands in a different way based on writing. See, even if this logic or this logic, whatever we shown earlier, is very similar. Is just straightforward similar. It's all about braces. That's all. But the whatever the tool understands is differ. So for the second case or this case, tool has formed a sequence of four gates, one after the other, where the timing of the complete circuit has been increased, and also the number of utilization of the gates has been increased, due to which, if so this is very small example, when you write some logic, so due to which you can understand, right, how the size of the chip varies and how the timing affects. See, whenever there is a STA engineer, they don't see some, there has been some setup time and hold time violations, or they have some timing issues where the chip is not meeting timing. They just come back at the RTL and say, hey, you have this block and this block is not getting the enough timing which we want to get. Then they ask us to modify the logic. Then we need to go through, understand where it is taking much time, what are the critical paths it has, then see where we can, optimize the logic. Then we do that. So this cycle will take some time. So because once the STA engineer come back and say, hey, I'm not able to optimize the logic, or once the PNR engineer comes and say, hey, I'm unable to fit in the chip, you just modify your logic so that I'll get enough space. Then RTL engineer again do the work, rework on the things. Then again the verification engineers, FPGA engineers, GLS engineers, DFT engineers, PD engineers, STA engineers, all these engineers times their work, the salaries of them, everything gets affected, right? So rather than if an RTL engineer do this work, writing the things in optimized way, writing the things in the very smarter way, by thinking it's very logically correct, then he himself can reduce the cost to the company. That's because the time taken to come back and do all these revisings will be reduced. So easy to market will be increased, and the profits also to the company will be increased. When see the to make the profits, there are two things. One is to you need to make by selling the products and all. The other way is in the R&D you need to cut down the cost. So if you do the things, the time of many of the engineers save, because the verification engineers, the validation engineers, the FPGA engineers, the PNR engineers, if you take at least five engineers a team, you have 5 into 10, 50 engineers of time, 50 into each of at least of 6 months, 56 year 300 man months of time, the resource cost and the salaries, everything is saved. And each tool cost for 6 months is very higher when you compare to the salaries of the engineer, right? So this all will be a saving if a RTL engineer performs his task very well and clear. Any doubts so far? So why STA engineers come back, why PNR engineers come back, and why RTL engineer need to fix? It's all because of how he code, the tool understands it, and by that it gives the synthesis. Am I clear?
Yes, sir, you are clear. Sir, in
Mhm.
synthesis, we will not get three input or four input AND gates.
Okay, that depends on the tool you use and primitives you have. Is there, the option is there, but the thing is, uh, this is the example I want to show you how that. See, this is very small logic which you can easily understand, right? But if you go to the bigger logics in the behavior model, you have multiple other things how you optimizely write it. So you will have, but not in the all cases people use it. Any other doubts? Here, my main motto is to understand what is the impact of RTL engineer role in the complete VLSI flow, and how it is, how he can perform the task so that many of the other engineers will not affect their jobs. So feel free to ask any questions apart from even onto the RTL side or VLSI side or about the companies, the hiring, trainings, and whatever you feel. Okay, we have enough time. Okay, even I want to take some as I'm continuously talking from last 1.5 hour. I want to take some break of 5 to 10 minutes. So meanwhile, you can shoot up with the questions so we can talk.
Sure, sir, you can take.
Yeah, meanwhile, if anyone has some questions, uh, I'll be online only. You can ask me. Not only the same topic which we are discussing, but if you have any other things also, of course, definitely not on the back end side because not on the back end side. I'm not going to talk anything onto the front end part or anything onto the mm, VLSI part. I'm open.
For students, what is the scope to get a job in design side, sir?
See, today at least when I see into the India, right? Uh, the design verification role, the DV, right? DV role uh, and the FPGA role onto the RTL role. These days we talk these all roles as an individual or different roles, but keep on going on to the next few years. We all call them as VLSA design engineers only. That's because we will no more put an engineer only for design, only for verification, only for validation. He needs to do everything. So now when we also see about Indian semiconductor mission started from Indian government, we at least foresee 50,000 to 1 lakh jobs onto the electronics industry, and out of which 15,000 jobs will only towards design verification roles. I mean the front end parts in India. So people, especially the new grads, definitely they have roles upcoming. But only the thing is, as I told you, right? Uh, People in this VLSA need to have patience. Is the very first level. See, as I told you, the chip itself takes 3 to 3 years, and you at least need to have 3 to 4 years to understand the complete things. Then you consider it as, then you consider them as a next level engineers. Till then, we call them as junior engineers only. So in the junior engineer level, people get lesser salary. But once you cross this boundary of 3 to 4 years, people definitely get a better salary when you compare to the software base. So these 3 to 4 years, they need to be understand things, they need to withstand, and they need to put more and more efforts to understand in VLSI is point one. And point two, critical thinking in the VLSI is very important because whatever you see today, it will not last for tomorrow because every day to day you will have new updates, you will come up with the new protocols, new design, new chip. See, because people expect many of the workloads need to be handled by the devices, right? Then if you want to process many of the workloads by the device, then somebody need to have that workload things, right? So of course the chips will come into the sector again. So many of the different implementation, different algorithms comes in, different kind of things comes in. So you need to implement different strategy chips, different kinds of functional chips you need to involve there, right? So definitely there is an option, but the thing is you need to, first thing you need to have patience and you'll get lesser salary compared to software engineer first 3 to 4 years. And the second thing is, as I told you, you need to have very logical thinking and keen interest and love towards VLSA or electronics. These two are the major things. Then everything will keep on following. And third thing, upgrade yourself with the new skill sets always in the VLSA. Then there is a definitely chance. And today we also foresee the requirement in the VLSA industry, especially on the DV domain, and even in US and few other countries also they want to cut down the cost and all. That's why most of the design verification roles, when compared to RTL engineer, design verification engineer roles, most of the things has shifted to India. And parallel, we have something from Vietnam also. Uh, but people in Vietnam is not so forward compared to India. So today we have most of the requirements in India. And definitely we foresee.
Okay, sir. Thank you.
Sir, you mean to say that RTL engineer and verification engineer roles will be clubbed in future?
Yes, definitely. See, the reason behind is I'll tell you. As I told you, everything is keep on changing. See, even our requirements, people is in this way, right? See, if I get a new phone, it has some issues. People want to buy some other new phone. They see they don't want to keep stucking with the same phone. They want a upgraded phone, and upgraded phone. So Samsung release some AI phone, then immediately they'll take it. If Samsung don't release that AI phone, there will be some other company coming in and releasing its phone. So who will be losing is this Samsung company. So what people want is first of all go to market strategy. That's what people want, right? So when these kind of things happen, people don't want to segregate the engineers because when AI pitched in, we all know that ChatGPT came in doing much of stuff. So in China, this incident happened where we have a RISC-V processor. RISC-V is very huge. Like you can build whatever the application you want. It's a open source. So if an engineer on the RISC-V want to develop something, he generally takes. If you have some 50% work also to implement one more 50% work, it will take some 6 months of time in generally. But these people from China has used the ChatGPT and built the same RISC-V processor in just 3 to 4 days with a team of 4 people. So if the 6 months role has came down to 3 to 4 days job, then there will be much more other things to take care. Of course, the new job roles will be created, but the thing is, these things will be come to the shortage. That's why. So they use integrationally the RTL, DB, and all. And this already happened. People are migrating between design and verifications, verification to design, and RTL engineer to FPGA, FPGA to RTL. This always happens. So knowledge existing into the Verilog, system Verilog, the design and all. It's all about how you think and how you verify and how you implement. That's all. So yes, definitely they will integrate towards same workloads because these are the regions.
Sir, generally, which domain will be having the higher packages, sir? Once they get
Okay.
experience about 3 to 4 years, either
Okay.
front end roles or back end in industry.
See. First of all, we need to know the exact difference between the front end and back end. We'll tell you in very shorter way. See, for example, you have a new design or new concept. Let us take you have same AI chip coming up. There is a non-AI chip and AI chip. Okay. When you come to the front end, there is a completely different. You need to implement everything newly. The logic is new. The RTL is new. The verification is new. The FPGA part is new. Everything is new, right? You need to everything do it from the scratch. Functionally, what is there, you will mimic. When you come to the backend, if the backend guy see on the two cases, he see only the gates, he see only the fits, right? He don't see anything. See, even if say A chip or non-A chip, he don't care. The whatever he changes is the technology changes, right? Whether it's a 5 nanometer, 10 nanometer, or 16 nanometer, that's what he sees the change, right? So if you ask me, the paying wise, definitely today PD engineers has bit higher pace. That is because the number of opportunities coming to the India for PD role is high and number of people available for the PD role is low. When the demand versus supply, when the demand is high and supply is less, there's the same concept, demand and supply rules. So when it is demand is high and you have lesser people, the packages is high. But if you ask me, both the roles will have similar packages, only a slight difference in the package. If there is demand and supply role are equal, then there is be no difference in the package. But the thing is, if you want to keep on upgrading and always think about new things and get the new things, you want to face the new challenges and do the new things, definitely front end will be the option. And if you want to get more and more and more expertise with the same thing, then back end will be the option. I hope I am clear.
Okay, sir. Thank you. Thank you.
Any other questions?
Sir, someone asked in chat box that
Oh, is it?
what are the skills required to work for SOC engineers?
Sorry, somebody else is also parallelly talking. If we can mute, you can please repeat the question because I did not see the chat. I am sharing the screen. Sorry, if somebody asks some questions on the chat, please feel free to talk. Sir, you can repeat the question again. For the SOC, that's what I remember. I heard.
For SOC side, what are the skills required to uh, join as SOC engineer?
Okay, so SOC, if you are talking about the SOC, I hope he is talking about the SOC verification only. Uh, okay, let me see the question. Uh, okay, the last one. Which skills should have for a student in order to work in SOC? See, in the SOC, see, SOC is a huge thing. SOC, whenever we talk about SOC, it's all about the product we are talking, right? So, system on chip, you have the complete system on chip. You have processor, you have GPU, you have memories, you have Ethernet, HDMI, USB, UART, you have a lot of things, right? So, when you talk about the fresher entering into the this particular front end domain, the basic thing, basic to the basic thing, he need to be very good at logical thinking, very good at logical thinking, because he need to think everything in a logical way, in the arithmetical logical things, he need to be very strong enough. Then the digital logic design, he need to be strong enough. These are the two basic things. Then on top of it, you will get into the Verilog. Earlier, people used to use VHDL, but nowadays no one is using VHDL. Even in defense sector, few people are still using, but even they are migrating to Verilog. So Verilog will be the basic thing. One more add-on. So once you have the digital Verilog and logical thinking skills, then additionally, what you want to have is the protocols. So what small, big, or whatever it is, the level of protocols on the embedded side is different. The level of protocol on the RTL side is different. So if you talk about protocols, there are vast number of protocols. You have on-chip protocols, off-chip protocols, serial, parallel. If you come into the sector, commercial protocols, communication protocols, a lot of protocols. So at least if a engineer, if a student want to enter into the VLSI front end, the digital design, logical thinking, Verilog, and plus add on to is knowing of few protocols, at least the smaller protocols like I2C, SPI, UART, USB. This one or two out of this is okay. SPI is also okay. And additional to this, I don't know how if your college supports system Verilog in some other ways, but having the system Verilog things also will be add on to enter into front end design verification or design or FPGA, these all things. Any other questions?
Sir, nowadays everything is going automation. Is there
Correct.
any chance to get out of physical design jobs due to automation?
Okay. See, I always say in other way around. See, for example, see, once upon a time we don't have Google, right? So if Google, let's talk the same AI jobs also. AI jobs also similar thing. See, automation is still exists in the PD domain or front end domain. Even people have automation. Rather than you are doing a repeated work, if that is a repeated work, people generally put it on automation, right? Even whatever the AI is doing, even before AI also, people used and using automation in the industry. So will this take off the jobs? Is definitely it may take off some jobs, but it will add only give some new opportunities also, right? So people should be ready to be migrated. That's what I say. It's not like whether your job will lose, but see, for example, there is an engineer. We will talk about two engineers. Anyways, I want to cover about AI also. So now, before example, I told you, right? Uh, in the China, they have did some risky thing. Rather than spending 6 months of time, you can do it in 4 days, right? If there is a person A and person B, okay, person A is keep on coding with his hand because I know this I don't know AI and all. If you give me some work, I'll be coding and completing it. Then he may lose his job. If someone uses the same AI rather than doing his job parallelly, he use AI and do if AI does some job to him and he does the remaining job. These kind of people will for sure get on the industry only. See, whatever the AI comes or the Google came in or the internet came in or whatever the tools come in, it's all about helping you to do your job simpler, right? See, for example, I always say this example. See, if you want to put the drill the nail in, earlier we used to have the hammer, then you need to beat it 10 times or 20 times so that nail will go in. Nowadays people use a drill bit. See, the tool has changed. So if a new person knows how to know, see, for example, new drilling machine came in, if the same hammer, whoever the person is using the hammer, he now learns how to use the drill bit, he will exist in the market, right? If the person say no, I don't know drill bit, I'll always use hammer, then people whoever want to get some person to the home, they'll not this get this person. Whoever upgrades to drill bit and use the drill bit and do that, people get them, right? In the same way, even in the industry also, whoever upgrades himself with the new technology coming in or new things coming in, it's all about the new tool helping him to do his work easier. That's all. So even some jobs go down, definitely the new opportunities, new jobs pitch in because day to day our requirements, the luxury, I told you, right? The luxury or the requirements of the human being has been increased. So we are not limiting, we are going to Mars. So there are much more opportunities to pitch in. There's always the skill set you have. That is important. I hope this answered your question.
Yes, sir. What is the scope for validation in India, sir?
Validation, definitely. See, nowadays I told you about Indian semiconductor mission, right? See, validation also exists in the India, but validation is very, very crucial role in complete VLSI industry because if some in the validation, right, you have two types of validation we generally talk. We call them as pre-silicon validation and post-silicon validation. Pre-silicon validation is the same design doing out on the FPGA. Post-silicon validation is you get the real chip after the tape out and you verify it if it functionally everything is correct or not. And also additionally, we have something called as test engineers. Today, their role in India was less, but coming up, if you see, this validation and test engineers will grow because once in next if within the 5 years or 10 years time span when you have all the fabs and packaging industries existing in India, people don't take these chips out of India to test it, right? People what they do once the fabrication is completed, they use the test engineers and all do some there is also automation exist, but they also do all the kind of testing. But there is also a issue with the automation for the test engineers and validation engineers. But compared to all, the number of engineers post silicon, I mean, under the validation are bit less compared to other roles. If you talk about only roles in the VLSA, you will find at least 20 roles. I hope I am
Okay,
clear.
sir. Thank you.
Yeah. Any other questions? It is 3:45 now. I'll take a break of 5 minutes. At 3:50, I'll be back, and we can talk remaining part on the RTL.
Okay, sir.
Yeah, thank you. Hi everyone, I'm back to the session. Please confirm me if everyone is available.
Yes, sir.
Thank you. Akash has raised the hand. Akash, please, you can go ahead. Akash, is this unintentional? If so, please let me know. Okay, thank you, no problem. So Prithvi has some question. Sir, is Xeon semiconductors are good semiconductor industry to learn VLSI related codes like SOC? See, uh, see, whenever you go to some company, it's not about whether the company is good or not. You just ask him what kind of Xeon semiconductors. Yes, I heard the name of the company. You just ask him like what are all the course or whatever the things he just covers. Okay, so based on that you can take a decision and you can go forward. See, here and there you generally always uh, see, as I told you, right, the skill set is important. So we always see there is a gap between industry and the college level, whatever the faculties are teaching. So if this gap can be reduced, definitely that would be a good option. But day to day, this gap has been increasing high. So I listened about some of the training institutes also. Even the training institutes, whatever they are teaching today, that itself is also not sufficient, and people want to get trained in the company again. It's again. So it's better you learn the see wherever you go. The fundamentals are very important. So you just see what those companies are, or whatever the companies you claim, whether it may be Sion or whether it may be something else. Just ask them what all things you will be covering in the training. Then you will understand the things. I hope this answered you. Okay. Uh, if you have anything else, people can ask me. Okay, I think this is not about mine. Okay, fine. So we'll jump back to our discussion again. Okay, onto the RTL. Then we will close the RTL related stuff within half an hour or so. Then I'll have half an hour more time. If you have any questions, we can talk. If not, we will close them. Okay. So, so that's about the introduction of RTL, the evolution of RTL, and if you see about the synthesizable of RTL and software coding, what's the difference? And in the software coding, it's all about you just write a logic. If the logic works, fine, that's okay. If you have a bug, just release a patch. Boom, it's done. Then people don't care of anything because fixing in the software is very easy, but coming to fixing in the RTL is very tough. We just saw some examples how it is affecting on the size of the chip, speed of the chip and all. Okay, so coming out to the parts of especially onto the RTL engineer, the main thing comes into the picture is finite state machines. Okay, or we generally call it as FSMs. So whatever the complex designs you have, okay, whatever the critical functionality blocks you have. Mm, it's all about you have something you need to be offloaded. That's what we thought, right? You basically know the functionality. Okay, if suppose if this happened, this you need to take care of this. If this happened, this you need to take care of this. So this you anyways have a systematical explanation, right? So that's where people generally talk about the FSMs. So FSMs is a finite state machines, where you all know about. I know everyone knows the FSMs. I know I'm not going much detail in whatever you discuss in the college level. We will go upper level onto the industry level, what you see the difference. So when you talk about FSMs, when you have the critical implementation things or crucial things, you generally go understand the flow. On the flow, you make a FSM diagram, and on the diagram, you will see if every corner of every scenarios has been working out. If it is working out, then you go and code it, right? So when you talk about the FSMs, so I'll show you one of the FSM's um, e PDF. Okay, so I'll just have a glance. I'll don't take much time in FSMs, but so this is one of the sunburst design paper which talks only about the FSM. If you just want, just go and type FSM sunburst paper, then you'll get most of the things inside the paper. So what this people did is they have different FSM coding styles. So whatever you take in the FSM, you code it. You have the present state, right? Like when you move from one state of the logic to another state of the logic, I'll just open in two other tabs so that you can easily compare the things. It will not take much time for me at least. Okay, I'll take one of the example. Okay, let's take this simple FSM. So this has four states, right? These four states, and you have a couple of inputs. Based on the inputs, you will go to the different states. Okay, let us take, you have state 1, state 2, state 3, and state 4. Zidil, read, DLY, and done. So if you want to move from one state to one state, you need to remember the states. So the remembrance of the state always happens, and based on what state you have, the remember of the states is always like a sequential circuit, right? You need to remember the state. And when you want to move from one state to one state, you will know the state, existing state, and if you get this input, then you will move the state. So it's a combinational circuit. This is the present state to handle the present state, and you have a circuits where you understand the logic of the state, at what state you have in the, with this state you get some inputs. Based on the input, you will get the next state, so that whether to move the state or not, you will understand. And being in the same state, okay, being in the same state, if you get the outputs, it's a Moore circuit. Or being in the same states, apart from getting the output, the outputs also depends on the inputs, then it's a melee machine. That's what this diagrammatical implements. So the means is, you have a sequential circuit, you have two combinational circuits. The sequential circuit is for the state holding and state movement, and the sequential circuits, sorry, the combination, both combinational circuits, one the before and one after. Before circuit is for to understand the state movement based on the input and based on the present state, and the other combinational circuit is based on the state. You need to give the output. In the more case, and in the melee case, you need to know the state, and additionally you need to know the input, then only you will go to the next state. Okay, I hope I am clear. So in the same thing, people starts using different kind of coding level, one always block, two always block, three always block, and all. So if you go in, if you see a bit zoomer version of this, let me zoom in. So you have four always block, one always block, two always block, three always block, and four always block coding style, which is nothing but whatever the three things we have seen. Okay. Um, that is the sequential circuits and two combination circuits. If you are coding in the same always block in the Verilog, we call it as one always block method. Instead of that, if you have two always block, one always block is for state movement, another always block is for outputs, and sorry, one always block is for withstanding of the state, which is a sequential, and the other two combinations are combined in a always block. We call it as two always block. And if there is a one three different always blocks, so that first always block will take care of combinational, sorry, a sequential circuit which is in the middle, and second always block is for the combinational circuit, to know based on the inputs and based on the state what would be the next state. If you see here, if it's a go, then the next state is read based on the size state and based on the input to predict the next state. And next always block is, if you are in this block, what would be the output. So this is one more block or the combination. If you make it as this way, we call it as three always block. And if you have four always block, it's for next movement of state, outputs, and mm, So one more thing is the sequential circuits and all. Then we call it as four always block. We very lessly use four always block. If you see here, all these four type of designs, functionally they are same. There is no difference in the blockings. Whatever the code, whatever the diagram we see here, functionally all are same. But to replicate that FSM in functionality in the coding style, one always block took 44 lines, two always block took 39 lines, three always block took 41 lines, and four always block took 50 lines. So the number of lines in the code has been increased. So people has done the enough research out of these always blocks. What is the best always block to use out of all the kind of synthesis things and all? If you see, one always block is almost 77% more coder than this three always block, and two always block, three always block is very near, four always block is much more higher. So the size of the execution, it will take more time, okay, when you do compile and things. So people has categorized all these four blocks according to the points, so easy to change state encoding. So when you are moving from other state to other state, now you have only four states. If for example it has increased to seven more states, okay, then how easily you can do the encoding and all. Everything has equally, there is no much more changes in the state, so everything has SSS. But if you have the coding styles also, it is same, it got everything got same points, but easy to understand the code. One always block is not that easy because you have all the combinational, sequential, two combinational circuits and one sequential circuit in the same block. So understanding is bit difficult when you compare to other blocks. So it got a minus point. And facility of debugging. Uh, so everything has under the same point. Yield effect synthesis, one always block has much more plus, but the two always block does not have, it has a negative point. See, yield, I hope you understand, right? So when you fabricate 100 chips, out of 100 chips, not every chip functionally is correct, right? You have some other issues when you do fabrication. So out of 100 chips, how many chips has functionally and workingly in all the term factors it is doing good, that is told by yield. So if I write using two always block, the yield effect results for the two always block is very negative when compared to all other blocks. That's what in the research they came up with. So people asked not to use two always block because the main thing is, if the yield has been decreased, so out of 100 chip you make, let us take you are making 50 chips, then only the cost or the cost burden of other remaining 50 chips will come on this existing 50 chips, right? So that's how the cost also increase and is very much headache to the company. So that's why people do not recommend to always block. That's the main reason. So in for the one always block, you have the issue of coding styles and how you understand the things, and easy to change due to FSM things, compared to one always block and four always block. Two and three always block are good. So when the people has compared one always, two always, three always, and four always block, one always block has issue with the understanding of the code. Two always block has issue with synthesis effect. Four always block always have the very higher lines of the code. That's why people has chosen three always block as the very uh, useful thing, and we need to use the three always block. See, if you see this example, the same thing of using 10 states. If you see the coding lines, two always block and three always block is very near 45 and 47, but the one always block went to 73 and four always block went to almost 60. It's very higher. And the same thing, the same understanding they have done with the that thing also. So first always block, second always block has some issues, but third always block you can see it's better. So same thing they have done with multiple FSMs. So this is one more FSM, bit more complex. So here also if you see 76, 73, and but the lines is 142, 100, which the 1 and 4 are higher, and two always blocks are very much near, and they performed all this kind of explicit testing. And here also if you see, three always block is performing bit better compared to all other blocks. And this is one more FSM, and they have done the similar analysis. Same here, the 3 always block got 92 lines only, remaining everyone is very very high, and one always block went to very higher range. And here also the results seem similar. 3 always block always wins the game. So the conclusion, people came up with a conclusion like it's always 3 always, when compared to all the things, 3 always block has less coding effects, and it is very likely to use. So people in the RTL side, based on the code you write, even the functionality is same, even the things are same, but the writing style is different, right? Even the writing style is different, the effects differs even in the results in synthesis, the results in yield and all. That's why a lot of research has been happened on this front. And as FSMs are the main and crucial part in complete designs, people generally ask us to use three always block style of coding. That's the main reason is this. Does anyone has some questions on FSMs or three always blocking style? I mean, any always blocking styles and all?
Janani garu raised hand. Is there any question?
There are two people raised their hand, Janani and Suresh Kumar garu. Okay, Suresh Kumar garu is different thing, and Janani garu, if you don't have some anything, please comment in the chat box, or you can also raise your hand and say. Or if you have any questions, just post it on the chat. That is also okay. Okay. Meanwhile, we will see if we have any questions by them later. And if somebody want to go through onto the FSM part and know much more things, if it is help the engineers or the juniors, sorry, the students and all, you can go through this document, understand and all. It's just you can type FSM Sunburst, then you'll get this link. You can open. This is very open. You can just go over PDF and see and come back. Okay. So now we'll go back to our document. So this is about FSMs, where the crucial designs or majority part we always deal with the FSMs. And the other important thing where people need to know if they're coming into the RTL is clock domain crossing, or CDC we generally call it as. So when you go from one clock domain to another clock domain, suppose you have different clock domains. Okay, uh, let us take, you have module A and module B, both are operating on different clocks. uh, in this way, let us take the same example. We'll remove these all things. This is all so let us take, you have module A and module B. You want to pass some inputs. Okay, between these modules, you want to pass some modules between A and B. For example, we talked, right, it's all about handling of data or passing of data between two entities. The entities can be two modules, two IPs, two subsystems, two SOCs, or whatever it is, right? So if you want to send some data from point A to point B, let us take from module to one module. Suppose this is operating at uh, 20 megahertz, and this particular block is operating at much more higher or lower frequency. Let us take some this 20, so you take it at 15 megahertz, okay. Or whatever it may be, the reading, right? You send it very um, high or very low. You can take 30 megahertz also. 15 is fine. Okay. Let us take. We are operating at different megahertz or different frequency bands, and if you are transferring some data, so whatever the data you are capturing, that will not capture at B, right? So what we generally do in this case, we generally used all this kind of CDC techniques. So CDC techniques also for basic thing, actually we have few of the direct links. Okay, we can discuss in that. Contact anything, even Maven will have. We'll take only diagrams. That's okay. We will not care about the content they have. Okay. If you see the CDC related things, right? When you're talking about two different clock domains, this has different clock domain, this has different clock domains. So when you're passing the things, this is the basic thing which everyone knows. You have two flip-flop synchronizer. You can always use the two flip-flop synchronizer to synchronize the data, which means you will not lose the data, but with some delay in the data, you will capture the things. So this is okay if you use a single wired thing, but it should not be continuous, and it should be a very long lasting pulse, saying that some interrupt kind of thing or resets kind of thing. Then you can hand over in the two flip-flop synchronizer. If it is a continuous pulse, then you will not get this time to stable in the two flip-flop synchronizer. That's where you have the different kind of things like multi flip-flop synchronizer came in, and you have a toggle synchronizer. And rather than this, we'll talk about the mux synchronization, where you have rather than sending off one particular signal, you can send a bunch of signals together based on the select line. So you will do the synchronization for the select line, not for the data. So based on the select line synchronization, the data whatever exists here will come onto the other side. Similarly, there is something called as handshaking mechanism. Whenever you want to send some data, you will not immediately remove the data from the bus. Rather than you say, hey, here you have the data with the request. So whenever the data has been captured with the acknowledgement, they say, yeah, I have captured the data. So that's how it's like a handshaking between two persons. So whenever the data has been captured, then again it will put a new data here with the request. So this is one of the other technique in the CDCs. And again, the other technique which you have is the FIFOs, where you have the asynchronous FIFO, where you write into this FIFO in the different frequency and you read from the FIFO at different frequency. In middle, you have a buffer, and a asynchronous FIFO in detailed discussion, it will take some amount of time, but we are just having a glance what type of different synchronization techniques you have. So whatever you write in a different frequency, and you do it at different frequency. That's how it's like a bucket. You just keep on putting in the bucket, and somebody else comes and removes one the bucket. But whatever you are putting into the bucket, or whatever other one is picking from the bucket, the frequency, or you know the speed, the both do's is different. That's all. So here also you just put a memory, we will push into this memory, and people who want to pick it, they pick out from this memory. That's all people generally do. This is one of the other CDC technique. Okay, how people handle the things. So clock domain crossing, whenever you want to transfer the data from one particular one particular domain to another particular domain who has different clock frequencies, then we do this. So these all kind of techniques will have their own research papers and the things. So people need to understand in and out to become a RTL engineer, so that whenever they comes this kind of issues or this kind of scenarios, based on that they need to understand whether you need to use a two flip-flop synchronizer or a mux synchronizer or a toggle synchronizer, or you want to use a FIFO in between it, or you want to use a handshaking mechanism into it. So based on that, it changes. That's how even in the protocols, even in the IP levels, the module levels, that's how people use it. So this is about CDC. If people have some doubts, we can discuss on the CDC. We'll wait for 1 minute here, and here I'm open for questions on the CDC. Based on that, we can dig in if time permits. We can dig internally also onto the CDC. So I hope there is no questions. So we will go to one more concept into the RTL design, the main thing. Okay. So as I told you, right, whatever the things you write, sometimes we are humans. At the end of the day, we make some mistakes. So that mistake may not should not cost you some other thing. So there is something called as lint tool, or we generally called as you need to perform lint. So what this tool does is it's a helping RTL guys, saying that whether you have done the all the kind of coding correctly or not. See, for example, I told you, right, if you don't write else case, compiler will take it and it will execute. At the end of the day, it will put a latch in the synthesis tool. That's how you'll get these mux followed by a latch. Then it is coming as an input back to the unconnected pins or the else cases, right? So that's how generally tool goes on. But if it could be wantedly or unwantedly, if you have some linting process will give this kind of violation, saying that hey, you did not perform this as per the expectation, saying that you don't know um, functionally whether the code is correct or not, but it says about the coding guidelines, saying that okay, this is the guidelines. If you put a if, you need to put a else. If you put a case, you need to put a default case, whether it's covered or not, whether you are making some mistakes in the common coding practices and all. This will help you to identify in the first level, rather than going to the synthesis, making it done, working. Then you see something in the FPGA side or onto the post silicon validation side. Then again coming back and all, to reduce this time and risking factors. People came up with this new tool called as a linting process, where you just run the code. If it has some uncommon things, it will put as errors. So based on things, RTL engineer will fix it. So this is about common or very high level points related to RTL. With this, we are done with the RTL. If you have any questions, we will take up on this. As we have some time, as the slides don't have it, but I'm okay. I'll show you some of the things on the verification part, especially on the how the UVM environment look like, how the how people generally do the verification and all. I'll give some light there. Before going there on the RTL part, does anyone has some questions? Whatever we had discussed till now.
Huh? Sir, can you explain any example to write the for RTL code and how to write it?
Okay, so that's what I have shown you in the FSM thing. So it's all depends on. Okay, I just had a glance. So if we want to talk about how you write the code onto the RTL, that itself need to have the knowledge on Verilog. So Verilog and what are the basic differences, how you write the Verilog coding and all. I'm not sure how many of the participants are aware of Verilog language. If we can know, then based on that, we can show a few codes, because before writing the code, we need to understand functionally what type of functional things we are targeting, so that we can talk on the coding part. Because if many of the participants may not know the Verilog, then we need to have a different session on the Verilog itself, because it will take some time to understand the few basic things. Because see, for example, even if somebody know Verilog, people generally say, um, uh, if you write a blocking, just a simple example, okay, if you have a blocking statement and non-blocking statement, people generally say blocking statement means it's execute serially, non-blocking statements means all the things will happen parallelly, but that's not true actually. So that itself have something called as stratified event queue. You need to understand what each happen in different regions. These kind of things, a lot of other things will come into the Verilog coding, then we understand the basics and all. Then we can jump onto the Verilog code, see what is functionally is expected, what we have done on the coding part. So, may I know how many of team here is aware of Verilog? Uh, Balaramurthy Garu has raised a hand. Sir, you can speak, please, or you can put your question or answer onto the.
Sorry, I'm traveling, sir. I'm not
No
able to
issues.
hear you properly.
No issues, Anil. You have some question?
No, sir. No.
Oh, okay, okay, no problem. So, so that itself will take a different time zone and day. So, anyways, in this part we can't cover it everything. So, apart from that, anyone have any other questions? Well, I'll show you. Okay, okay. So, whatever the RTL you write, people we generally call it as DUT. The name infers design under test. So whatever the RTL people write, earlier different companies used to follow different methodologies. So as I told you, right, people always use, even today people are using Verilog only. We also got something called as HLS, high level synthesis, where you write in C or C++ code, that there will be HLS tools to transfer that C or C++ codes to Verilog, and we after Verilog to synthesis we have other tools to make it. So rather than writing in Verilog, if you write in C or C++, it will directly give a synthesized netlist. So there are tools like this, but they do not perform very optimized way, and people this is still in research level from past 5 to 7 years, and still people are not ready to use HLSs. Uh, but coming on to the other side of the verification part, as only this will be the synthesizable part, whatever the verification bench or verification environment, that means is the DUT performing correctly or not, you pass some inputs and check the output. So to pass some inputs and check the output, that necessarily no need to be a synthesizable one, because the synthesizable one is DUT or RTL only. So there people have came up with the new versions like system verilog, where you have oops concepts has been involved like a C++. Similarly, they done the verilog and system verilog. They introduced some oops concepts so that the testing side or the verification side, rather than performing the same task into writing the code copy paste and doing it multiple times, they use classes and objects to make it robust or easy of using for the employee, for the whoever is the engineer. So after that, the issue with the SV or system verilog is you will write the code, but between companies to companies, if a new person joins in the company, he don't know the complete verification flow because it will be too different between two different companies in the implementation. Even if you go between two different designs also, it may differ. So if the new joinees or the new people whoever join the team, or if you shift the company, and the easy to understand between two other engineers inside the company also, it is difficult because whoever wants in their way they write it. So people want to make some systematic way to it, so they bought out something called as methodology, saying that you need to have this kind of blocks if you want to do verification. So whatever the DUT it is, what functionally it can be Ethernet, USB, UART, SPI, to see whatever it is. But the common thing is to pass some send some sequences, or to give some inputs. You see, for example, you have a AND gate, okay, or you take a adder, you have A and B two inputs, C as a output or a sum as a output. Okay, so you pass A and B. For even A and B, you need to pass different sets of inputs randomly. Sometimes A can be 3, 5, 6, 2, 5, whatever it is, and in the same times B also can be of different combinations or permutations. So all these combination and permutations, basically the sequencer gives to the driver. So the driver need to drive it onto the interface, which means the A and B ports. So whatever you are driving, you will record it and you will send to the scoreboard. And whatever you get as a output for the past input, you get as a output from the DUT, that will be monitored and given to the scoreboard. And there will be called as one more referral thing. If you pass this input, we call it as a reference design, which is not there here. Okay, so there will be one more block. Same inputs, whatever you are passing will be passed to that reference design, and it has some output. It says whatever you pass here, this is the expected output. And if that expected output is coming from the output agent, and if the both matches, then scoreboard say yes, the expected and the actual one is passing. So that's how wherever you have these blocks only. They made a methodology kind of thing. Generally, we call it as methodologies, the UVM or OVM. So they follow this kind of blocks or this kind of steps only, uh, so that even a new person, a new guy or new teammate comes in, everyone follows the same thing, so he can understand from where they are driving, from where they are checking the inputs, where they are giving the inputs. So this would be a easier way. That's how people do this. But not only this, there is much more things involved in the driver sequencer, monitor and scoreboard. But to understand you on very brief and very top level, I am saying this. Okay, so that's how people use these kind of blocks and perform the inputs and outputs. So once the sequencer have the logic, like for example, you have 4-bit input for A and 4-bit input to B. So combinedly 2 power 8, 256 combinations you will get. So all the 256 combinations is verified or not. So we have functional coverage, code coverage and all. If this functional coverage says about whatever the functionality of the chip, like you have these inputs, if you pass these inputs and you say addition, it need to do addition. So functionally this all will list down, and we will do all the tests saying that okay, you need to pass this many number of random inputs, this is all the test. Whether you performed or not, we'll check all the tests. We call it as functional coverage once it is 100%. And one more thing, we call it as code coverage, which means if you write all the if and else cases, for example, whether all the lines of the code has been executed at least once, we see that. And if both the coverages are 100%, this says that 100% testing of design verification engineer has been done. Then only it will go to the final approval stage to the backend and all. So that's what the environment looks like in the verification part. So this all comes onto the verification environment front.
What is the main difference between UVM and OVM, sir?
It is just a structural difference. See, when you see just uh, UVM and OVM, I can show you if they have some structural difference. So UVM, OVM, RVM, everything is same. They generally make some fixed kind of things. The sequencer, driver, monitor, these things are a bit difference in OVM. That's all. I'm looking for some diagram. It's just a verification methodology. That's all. But everyone uses system verilog at the end of the day. But how you put, where you put the systematic things differs. That's all. Whatever you write the code inside monitor, driver, sequencer, or some other block, it's all in the system verilog only. It's not a new language. We use the same language, system verilog, and we form something called as blocks. And each block has its own responsibility in the verification environment. So the name of the blocks and the different blocks in the UVM and OVM differs. That's all.
Sir, can you differentiate SV and UVM, sir, methodologies?
SV is not a methodology. SV is a language. So when we want to differentiate between Verilog and SV, you will. So Verilog is a language, SV is a language. Whatever is applicable in Verilog is completely available in SV also. Additionally, on top of it, we have non-synthesizable variables in SV, something like classes and objects, which will be used. This is all from the OOPS concept, which will be useful in the verification part. And you use the same SV code for the verification, but the only thing is how you verify in the systematical way. We form something called as methodology, where we formed a fixed blocks like this, saying that each block has its responsibility, and you use system verilog code inside the UVM. That's all. UVM is not a code; it's just a methodology. Any other questions? Okay. Uh, that's it from my side. So I have completed this particular session. So I have some 25 minutes of time if I'm not wrong somewhere. So if you have any questions, you can talk to me. Feel free to ask, even it's a smaller doubt also or smaller question also. Or if it is apart from RTL also, I'm fine. You can ask me things. I can tell you. I am open for questions. I'm just curious to know all the 64 attendance years are completely faculty.
Yes,
Yes,
sir.
sir. All are.
Okay, so this college has 90 plus faculty only into the
It
electronics
is
domain.
from whole India, sir.
Okay, and not from your college alone.
Not from our college.
Oh, okay, okay,
Sir, from host institute, 20% of faculty are there, sir. Remaining all from different institutions.
okay. Fine, got it. So feel free to ask any questions. I'm open onto the semiconductor domain. I can wait for 5 more minutes. If there are no doubts, we can end up the session here.
Hello, good evening, sir.
Eh, yeah, good evening.
Sir, can you give a brief just on research topics in
Okay.
this domain, sir?
Okay. So, yeah, thank you. So there are a lot of scope onto the research, and so especially if you talk about the research, I can say the front end has many things. See, for example, uh, the all the algorithms. So whatever people make it into the software, at the end of the day, people need to make it into the hardware, because see, when you compare to the software, hardware is very speed, or uh, you know uh, very high in speed. People everywhere need to have they want the quicker answers always, right? So all the computational things today takes the very primary role onto the things. So for example, let us take very smaller thing to understand. Mm, See, if you have something to algorithm to search something, okay, you have some huge database. If you want to search something, people generally use different algorithms to do that, right? Those kind of algorithms you can bring back to the hardware itself, so that rather than you pulling out uh, to make something in the software, you can do the same thing in the hardware, right? So these kind of things, especially the computational side, the processing side, and how you make something in pipelining, and how you offload something, people are very much keen into to do that. And moreover, when this AI algorithms came in, all the AI algorithms or LLMs has been running in uh, so-called software only. So it's taking more and more time to analyze the data and come back. Rather than doing that, if those things came into the hardware, it will be much more simpler and easier, very speed compared to software. So these kind of things people are much more interested today is one thing. And second thing is all about the automobile industry. The autonomous drivings and all is one more keen interesting people are looking forward. I hope this answered your question.
మెసేజ్ చేశాను.
Yes, sir. Thank you, sir.
Thank you. Any other questions? So if there are no more questions, we can end up this session here. The host, whoever is taking these sessions, please you can take a handover. Thank you very much for everyone to for the participation. Thank you.
Thank you,
Sir,
sir.
once
Yeah, please. So someone is asking some doubt before that. Yeah, please.
1 second, sir. Now I would like to request our coordinator Krishnaveni Garu to give the summary session.
Thank you, sir. Thank you, Raja, sir. On behalf of Department of ECE, Gayatri Vidya Parishad College for Degree and PG courses autonomous, I would like to extend my heartfelt thanks to your insightful and engaging section on the VLSI design cycle and roles of verification, sir. Your detailed explanation about the design flow, verification processes, and more emphasis on the critical roles and collaboration between the design and verification engineers provided us valuable insights, sir, and especially real-time examples and practical approaches. You shared resonate all the participants and help to bridge the gap between theory and practical approach, sir. We are really appreciate your time and effort and expertise in making this session a grand success. Thank you so much, sir.
Thank you very much, Andy. Thank you all.
All the participants be in mid. Our second speaker will start soon. Within 1 minute, he will join. Sir, Raviteja Gara, are you there?
I request all the participants, please switch on your cameras. We'll take a group photo. Raja, sir, uh, Please switch on your camera, sir. We'll take a group photo.
రాజేష్ సార్ లెఫ్ట్ అయిపోయినట్టున్నారు మేడం. రవి సార్ జాయిన్ అయ్యారు. రవితేజ గారు,
Okay.
సార్ రవితేజ గారు, ప్లీజ్
Yes,
switch on
yes.
your camera to take a group photo.
Okay, now I need to switch on. Okay, just give me a minute.